Yeah,
Okay.
so great. The next talk is by Chris Henson, talking to us about some feature of CSLib, which is that great new thing this year, which is a computer science library. And yeah, I let you tell us about it.
All right. Thank you so much. So since Fabrizio was so kind to give us a sort of overview talk of CSLib yesterday, I'm gonna jump right into talking about our formalization of locally nameless Lambda calculi. So I'll get into what I mean by locally nameless in a couple of slides, but just sort of an overview first. So what we have here is untyped terms. We have the simply typed lambda calculus, and we also have system F with subtypings. That's when you add in typed variables. So we have proofs of progress, preservation, some starting work on confluence. And so the thing that's interesting to talk about here is not so much what we're formalizing, because this is, pretty well trod in other proof assistants especially. But there's some interaction between this style of locally nameless that's not so common to formalize, especially in Lean, and Lean's metaprogramming capabilities and the new proof automation with grind. So the stat that I'm listing here that I think is interesting is the system F formalization compared to some prior work in Rock is about half the lines of code for something that's very closely follows. So I tried to make it as apples to apples as possible there comparing. Um, so I'll talk a little bit first about, how we formally represent the lambda calculus in a proof assistant. So here I'm just talking about untyped terms at first, so we just have abstraction and application. And so informally, we talk about this idea of terms being alpha equivalent, that they're the same up to using different names for variables. And the problem is if you try to, formalize this and you use strings as binding, then this alpha equivalence is not definitional equality in Lean. And really informally, we treat these like they're equal. So this is a very old idea, really dating back to the birth of proof assistance and automath, this kind of thing, of instead using indices. So instead of literal strings, we use these natural numbers to represent intuitively how far away we are from the corresponding binding. So this is a lot better formally, but it's still not really perfect. So one of the problems is if we go to do something like substituting in a term that has additional binders, we have to do this adjustment of all the indices of shifting them forward to accommodate. And so I've formalized to this style in Lean before CSLib, and the problem is it's just very low level manipulation, kind of like the last talk of talking about tactics versus very low level proofs. So one alternative, and there's decades of research this, right? It's not a new idea, but one approach is to syntactically divide up free and bound variables in your Lambda expressions. So you may actually be familiar with this if you've touched on any lean metaprogramming in the past. You see this reflected in the lean dot expression type that's mirroring what the kernel does. So what I mean by locally nameless is that we've got one constructor here, this bvar, that is natural number indices, like I was describing, but we have a separate constructor for some type that we're using for free variables. And so this is exactly how we're defining things, untyped terms in CSLib. The primary difference here is that we're polymorphic over the type that we're using for free variables. And so what we're expecting free variables to satisfy when we're actually proving theorems with them, it makes sense that you should have decidable equality on them. And there's this class in CSLib that Fabrizio actually mentioned yesterday. It's just a computable version of the infinite class that's somewhat convenient to use. So it's just saying that intuitively, just like strings behave as names, that I should be able to take a set of names and get some new name that doesn't clash with this. So there's some nice things that immediately happen when we have this distinction between free and bound variables. For instance, now it's very easy to now I have an example here of a function where you can very directly extract free variables out of an untyped term, and this turns out to be very nice. And similarly, our idea of substitution is also split into free and bound. So for bound, it's standard to call this opening, and the idea is just very simple. We have some index I, we're wanting to replace that binding with some new term. So we recurse through and we make that replacement. And then it would be the very same idea for substitution, except we're just ending off on the free value piece because we know there's decidable equality there as well. So these are the things that get simpler. What is a little more complex is how we're dealing with abstraction in some of these more derived things on top of terms. So we have this idea called cofinite quantification. And the intuition is that if I'm wanting to write further propositions about lambda calculus terms, for any of the cases that involve binding, like an abstraction, I'm going to characterize this in terms of if the body satisfies this proposition when we do substitution, then I have evidence that it's satisfied for the abstraction. So I know that's a bit of a mouthful, so let's look at a very simple example. So we have this idea of being locally closed, which is just saying that a term is well formed. And the idea is that on its own, a single index, a bound variable on its own is not well formed because it's not paired up with an appropriate binder, the lean terminology, right, of loose bound variables. But if I do substitution with this and I substitute a free variable, then a free variable is just, it's just a name, a placeholder, and this is well formed on its own. So what we conclude from this is, yeah, this identity function, lambda x, return x, is well formed because its body is well formed once you do substitution. And so you can see why I didn't, lead with this definition because it takes some adjustment to get used to, but it's exactly what I've expressed in this example of we're providing some set of variables, which in the example above was implicitly the empty set. And I'm just saying if I do any substitution, bound substitution, so we have this exponent notation we use for the first binding, saying that as any of these substitutions, I get a well-formed term, so this is proper to use as the body of a lambda expression. So this appears not just for well-formedness, but anywhere where binding shows up. So for beta reduction, for typing derivations, and for the more complex formalization of like System F, this appears also for type variables, for let bindings, this sort of thing. And I list some references here because I know that's very much not convincing to get your head around this and the compactness of a talk, right? Okay, so this is the main part that we're going to talk about, how this interacts with various things in Lean. So again, you can kind of imagine these proofs that have this aspect of needing to select a set of non-clashing variables. Non-clashing with respect to whatever terms or types we're dealing with in a proof. And it's not quite as bad as dealing with natural number indices, but it's still pretty low level. And so the thought process is, well, we should be able to do some sort of automation around this. And so the prior work in this area does exactly this, but has some limitations. So prior work has tactics that are designed for this, but have to be specialized to each type system you're formalizing and don't have much control over how you're doing this calculation of free variables. And this is really unsatisfying because intuitively, we should have this idea that the only difference between each type system is it's just a different list of functions for extracting these free variables. So thinking about formalizing this in Lean, my thought process was, well, in Lean, we have the ability to not just write automation through tactics, but we can also write pieces of syntax that expand into terms. And so I'm going to have an example in the next slide, but the intuition here is that we write this term elaborator. That's a piece of syntax you write in place of a term, and you give it a high-level specification of what it should avoid in terms of free variables, and then it will compute this from your hypotheses that are available. So here's the example I promised. The theorem itself is not so important. It was just the shortest example I could find. So this is an excerpt of a theorem saying that when you do beta reduction, that we maintain this well-formedness property. What's important here is this highlighted portion here. So this is the part I'm talking about of if you were writing this by hand, I would need the free variables out of the body of the lambda term, and then the free variables that were used in this proof that that really is well formed. And we're passing it to this fresh exists theorem, which is just this is just forming the existential, passing, creating this fresh variable in the proof that it doesn't intersect. So in CSLib, instead of writing this low-level list of free values and fin sets, instead we have this term elaborator, free union. And the idea is that I'm passing to it. So var there is the type of free variables I'm using. So these are terms that have this type var as free variables. And the brackets there is where you're passing in your list of functions that you should use for extracting free variables. So it's the same one I showed on an earlier slide that's just taking a term, extracting out its free variables. And the term elaborator also implicitly includes if there's any just single variables or sets of variables, it'll throw them in there too by default. So what this is literally doing, I don't think it's instructive to show the metacode, but it's very literally doing a for loop through all of your hypotheses, and it's seeing that you have a term m and including those free values of m that we were doing manually before, but it's also taking the free values out of the thing we're substituting in, the n. So it's kind of casting a wider net because we know if we include some extra free variables, it's not going to break anything, basically. So jumping ahead a little bit, the other nice thing about this being a term and not some tactic is that I can actually, pass this to grind, and with the other annotations we have, this is the full proof here. It closes everything. So this is a pretty simple idea, right? We're just, looking what's in our local context and interacting, with the free variables here. But there's a lot of well-crafted complexity of Lean's metaprogramming system that has to come together to make this work and to make it work and be a good user experience. So, I mentioned type classes here that it's both, synthesizing the decidability during the term elaboration. And then since it's elaborating just into a normal term, it's able to interact with the other has fresh type class, and you actually get informative error messages out of this if, like me, you forget to add a type class parameter. And it's properly resolving all of these things, like, we're polymorphic of the free variables. It's able to take a type level argument. And you might have noticed that namespacing wise, I passed an unqualified name to that list of things we're going to use to calculate free variables. And so where this really sticks out is actually in the more complicated type systems where we have a lot more different ways to extract free variables. So for System F, there's at least 6 distinct locations you could get free variables from, because we also have typing contexts, and then for terms and types, we have type variables, term variables, and there's term annotations too. And just in general is, an improvement because there's one unified way to do this through all of the formalizations. This is shared between all of the locally nameless formalizations, and it's technically not even specialized to Lambda calculus. I just don't think it would be very useful for anything else. And like I said, compatible with automation. I was going to briefly mention this one other piece of metaprogramming we have. So this idea we had a while back was that we wanted to standardize how we were talking about notations for reduction in CSLib. And so what we ended up settling on is I wrote this attribute with much help from the Zulip to be able to, you annotate something that looks like a relation, and you give it what symbols you'd like to use, and it creates these parameterized arrows. So we had decided on at the library level these couple of arrows for reduction and for the reflexive transitive closure, and then the user provides what they'd like to further notate those arrows with. And so this again isn't just for the Lambda calculi. There's combinatorial logic using this, a similar system for labeled transition systems. So it's kind of widely adopted. Okay, so this lets me segue into talking a little bit closer to grind. So one of the kind of design philosophies we have, because as was mentioned before, we are downstream of Mathlib. And so one of the things we really tried to do is reuse as much of the existing Mathlib infrastructure as possible. And one of the places where that worked out really well was for the definition of locally nameless typing contexts. So a typing context, as we've written it out, is just a list of pairs. So the first component is your free variable, the name, and the second component is just what type that you're ascribing to it. And so what turns out to be really helpful is Mathlib has this existing module, list.sigma, that treats lists of dependent pairs as essentially key value stores. And so when I was first doing this formalization, I upstreamed to Mathlib just a couple of tiny lemmas about how duplicate names and stuff works, and added the first round of grind annotations to that module. But with that established, past that, we don't really add much additional definitions at all to this module. I believe there's literally 2 definitions we add, and they're just notational convenience things. But what we are able to add additionally, because kind of the CoTool system, ecosystem that was talked about earlier today, because you're able to use attributes to add grind annotations. So we already have the upstream grind annotations that exist. And we also add into this namespace of context some scoped grind annotations. What's nice about that is that they're a little more aggressive than might make sense more broadly to be in Mathlib or too specialized, but they're only activated if you're specifically in this namespace or open this specific scope. So this is kind of another design philosophy we have of very aggressively using scoping, using namespacing, and we even have some environment linting that checks for some of these things as well. Okay, so now moving into more of talking about grind. So there's just some stats and history up here. So we started using grind relatively soon after it was released, that I ported over simple types and had been using System F from the beginning there. And just wanted to point out this ratio of, so it's something on the order of a couple of thousand lines of code for all of these type systems that we have so far, and 250 uses of the grind tactic. So that's pretty dense for that amount of code. So I thought a while about how I wanted to, display this, because I cited earlier, how much shorter some of these proofs are, still with some trade-off in performance, but so it's kind of difficult to show this on slides, right? So what I figured on is this last bullet point here. So there's actually some interesting interaction between what we've talked about with this cofinite quantification piece, and the way that grind works with its e-matching patterns. And so there's a little bit of incompatibility there, but enough flexibility in grind to get past this, and I think a kind of interesting user experience story. So just a reminder, I've thrown up the definition here again of what well-formed terms look like for abstractions. And the important piece here is that this constructor is leading off with a piece of data, something non-propositional. So you're having to preside this set of finite variables, and then you have to prove this propositional piece about all of the openings being well-formed as well. So I'll actually start this off by talking about another piece of automation. So again, we are downstream of Mathlib, so we also have access to ASOP by default and make use of this as well when it's appropriate. And so if I'm using ASOP here, I could actually tag this entire inductive with the constructor's rule builder, and it won't complain at all. Or I could tag, as I have in the example here, I could tag this particular constructor as a forward rule. And I've sort of set up this example to show that, in this situation where I've given it exactly the goal of showing that an abstraction is well formed, and I've given it the exact finite set it needs to use in this cofiniteness condition, that ASOP is, so my intuition, and forgive me if I'm speaking correctly about any internals here, it's not my area of expertise, but my intuition is that it's, looking through the hypotheses and is able to see that this finite set is the correct type. And so add this, to building up this application, see this cofiniteness condition, and ASOP is able to close this proof. In contrast, this type of constructor, any of the cofinite constructors, do not allow for valid e-matching. And the intuition of this, without getting into too much detail, is that you're asking grind to essentially select some sort of data. And I think for very good principled reasons and for performance, this doesn't make sense. So the example that you see on the Zulip occasionally is that people are surprised that grind can't solve certain existential goals. So this is sort of an analogous issue here. So the question is, what do we do about this in this library? Because the cofiniteness piece is pretty essential to this binding scheme, right? So here's where I'm going to show an example, kind of two birds with one stone thing of this is an example of a proof that's drastically shorter. So in some formalizations, this could be, somewhere between 50 and 70 lines of a proof this is System F now, saying that if I have a typing derivation in System F, just all of the components are well-formed. So we talked about well-formedness of terms, and then there's a corresponding notion that I didn't define of context and types with respect to a context being well-formed. So you can see the outline of this proof is we're inducting on the typing derivation. And first, the highlighted portion here, we're using the term elaborator that I described earlier to create this set of free variables that's not intersecting with anything else in the context. And if you look at the bottom, you can see there's an all goals grind. So the uninteresting cases that don't have binding are immediately solved by grind by essentially doing a case analysis on how types can be well formed. But there's all these other cases that involve binding, so abstraction, type abstraction, let binding. So what do we do here? So these highlighted terms are all involving these constructors that have a cofinite aspect to them. And so while these aren't valid grind rules, if I take these theorems and partially instantiate them with the set of finite variables that I constructed with this term elaborator, then I'm left with something that just has propositional hypotheses, essentially. And so this is a relatively new feature of grind to mirroring a behavior of simp that I can pass in, a partially instantiated theorem like this, some arbitrary expression, to tell grind to use this. Earlier in the development, you might have seen people using the have tactic to put these kind of things in the context. And so with this, this is how grind is able to close all of these goals. I just have to give it this little bit of a push in terms of providing this data to it so it can get to the propositional pieces. And so what's the interesting lesson to learn here, right? So kind of taking a step back from ASOP or grind or any particular tooling, I think it's helpful to think about what would you expect any piece of automation to do if you were expecting it to select these finite sets of variables. Well, exactly what's required here to get to the propositional piece. You're somehow expecting a piece of automation to essentially, derive this entire term elaboration selecting free variables piece, which is really like the content of the proof. It's not a structural property of any of the types you're using. So kind of my perspective here is that it's almost kind of nice that this principled approach of that it's not trying to select data in this way because it makes you step back and think a little bit in terms of, it makes sense in terms of having an outline of a proof and providing things that are just structural in this sense. So it's kind of the interesting piece of grind interacting with the cofiniteness. And then just lastly, I was going to talk about some of the future work that I have planned that's related to this. So I'm not intending to have a standardize on locally nameless binding for all across CSLib. There are definitely trade-offs in terms of the complexity that's involved with the cofinite piece, and especially certain proofs are just harder to write in some ways. Some are easier, some are harder. So what I'd really like to do is take inspiration from other proof assistants, specifically in Rock. There's AutoSubst, in Isabelle, there's Nominal, and these are all systems where you do some variation of kind of a high-level specification of a type system, and it does the work of generating a lot of the definitions and tactics that you need to work with. And so I think there's a lot of room with the flexibility of Lean's metaprogramming system to do something kind of new and interesting here. So this is very early work. I've only just played around with it a little bit, but this is on my mind for the coming months. And then additionally, we don't have much of anything in terms of semantics. So there's denotational semantics, for instance, and this is again a case where it's nice because upstream in Mathlib we already have omega complete partial orders, for instance. We have category theory in Mathlib. I think. I'm very interested in categorical semantics ending up in CSLib eventually. I think there's some harder technical issues in making that work, but I hope we can figure it out. And then lastly, I mentioned very briefly that we do have some proofs related to confluence. And so recently at the Italine meeting, this expanded a little further. So we added some of the generalizations of confluence, semi-confluence, this sort of things, but the commuting versions of them. And also some properties of terminating relations. What I'd really like to do next in this area is there's this concept of general term rewriting systems. And this is inherently built on model theory. So what I'm hoping is, again, is that we can reuse some of the existing model theory library in Mathlib for this. And then just a couple of thank yous. I mentioned very often prior work in Rock. I highly suggest this is actually a POPL tutorial from 2008, but I think the documentation holds up and was something I referenced a lot. And I'm in Philadelphia, right down the road from University of Pennsylvania, so those folks have been very welcoming, and I appreciate that. And then just thank you to several members of the Lean FRO who have helped generally with CSLib and with aspects relevant to this particular presentation, and of course recognizing all of our sponsors and partners. So thank you.